I'm not here. You guys have probably seen this Monday. I don't know. Maybe some of you keeners are looking at this on the weekend. Anyways, this is Monday's lesson. If you had questions from the assignment from the previous day, email them to me, or keep track of them, because I'm not going to be doing any work over the weekend. So keep track of them. We will address them on Tuesday if you have. Remind me, because I might just jump ahead, because that's kind of how I do. Anyway, so this is the first page of notes, and you can just pause this because I'm recording it, so you can pause it, write it down, and then unpause it. Okay, so you just finished writing the notes down. Now I'm going to talk about it. If the net external force on an object is not zero, the object will accelerate in the direction of this net force. So if the net force, I keep using my bottle of water as an example, if the net force on it is just 1 Newton, from the left, from the right, whatever, the net force, so all other forces are kind of canceled out or what have you, it will accelerate. 1 Newton, it's going to accelerate slowly, but it will accelerate in that direction, all the more so if the force is higher. The magnitude of the acceleration is directly proportional to the magnitude of the net force, which is what I was just saying. Small force, it'll accelerate smallly. Big force, and it'll accelerate bigly. I'm making up words here, right? You know that these aren't scientific words. Inversely proportional to the mass of the object. So if my water bottle is full of lead and I'm applying 1 Newton of force net, it's going to accelerate that much slower. If it's 1 Newton of helium, or 1 Newton of helium, excuse me, if the bottle of water is full of helium, way lighter, the mass is way lighter, it's going to accelerate much, much, much faster. Think if you've ever pushed a car that's stuck in the snow. The bigger the car, the harder it is going to be to push the thing. Priuses are very light, by the way. So here's an equation that we'll use for decades to come. Force, net force, equals mass times acceleration. F equals ma. Force is measured in newtons. If the net force increases and mass is constant, then acceleration increases by the same factor that the force increases. If the net force of an object is constant and mass increases, then acceleration decreases, again, by the same factor. Hopefully that makes sense. Little diagram here for you that basically just kind of goes over what I was just saying. If you look at this, big acceleration, big force over here, there's a lot more mass, so the acceleration is going to go down when there's less force, and so on and so forth. All right, hopefully that makes sense. Oops. Oh yeah, we are doing this. Okay, gravity and pulleys. Okay, write this down. Good, you wrote it down. F equals ma can be the same as F equals mg. A pulley system complicates acceleration. The leading weight is the one that provides the applied force, and we're gonna do examples, so you'll see. But the total mass must be used for the F equals ma equation, and both masses move at the same time because they're attached. This probably doesn't make any sense at all because you don't have an image to look at, but we'll definitely go over it. So maybe refer to this after I do the kind of second page of examples. We're going to do practice questions from both of these pages, and this is your assignment. Good, glad you wrote that down. Now let's go to examples. Where is the... There she is. Okay. So from page, let's start with where are we at? Page 133. We're going to do some practice questions. Let's start with number 1. A net force of 126 newtons south. So F equals 126. It's going south. I'm not writing the units because it's kind of assumed, but we don't know the direction, and this might change things. Acceleration might be the opposite direction or something. Force is 126 applied to a 70 kilogram sprinter, so mass equals 70. Determine the acceleration of the sprinter. F equals ma. It's just the three variables. Force is 126, mass is 70, so we have to solve for acceleration, divide both sides by 70. 126 over 70. I could do that in my head, but it'd be showing off. Just kidding, I can't. 1.8. Actually, I probably could if I took some time. 1.8. So acceleration equals 1.8 and 2 sig fig. Oh, 70. 1 sig fig. So the textbook's got it wrong here. So acceleration should be 2 meters per second squared south. It will accelerate in that direction. It's disappointing when the textbook gets that stuff wrong. It happens. I had this kind of side gig for a little while, reading through new textbooks. Does that sound exciting? But looking for errors, and they're there, but I guess they're not all caught. Anyways, page 133. That's number 1. Let's jump to number 3. This one says, a cyclist starts to pedal vigorously, increasing her velocity from, okay, so increasing. So we're starting with VI equals 6, and it's going east, so 6 meters per second east, to 14 meters per second east. So initial is 6, final is 14 in 6 seconds. So the time equals 6. The total mass of the cyclist, so M equals the cyclist and the bike, is 58. Find the net force acting on the cyclist and the bicycle. So F equals, this is what we need to find. Notice they're giving us this nonsense. So we're going to use those 5 equations. 5 key equations of accelerated motion. So what we're going to need to do before we can get the force, we need to find the acceleration. So we don't have displacement, we don't need displacement. So we're going to use the second equation. So VF equals VI plus AT. VF equals VI plus AT. I feel like I'm talking fast. I've got nobody to slow me down. Pause this if you need to. You can replay it at your leisure. But basically, it's asking for force. It gives us mass. It does not give us acceleration, but it gives us enough stuff to find out acceleration. So that's what we're doing. So we have to find that out first before we can get force. Final velocity, 14. Both going in the same direction. That's good. Nothing has to be negative. Initial, 6. Plus, yeah, we don't have acceleration. And then time is 6. 14 minus 6 is 8. 8 equals 6a. Divide both sides by 6. 8 over 6 is, what is that, 1.3 repeating. Acceleration equals 1.3 repeating. That's why I like fractions, because this doesn't go well in the calculator. 4 over 3 does. So now F equals ma. We want to figure out force. Well, mass is 58 times acceleration, which is 1.3 repeating. That's important. If we just punch in 1.3, it might give us a goofy answer. So what I will often do is I'll just do like 4 divided by 3 to give myself the 1.3, or 8 divided by 6. It's just same thing. 1.3 blah, blah, blah times 58. 77 point blah, blah, blah. And we're going with 2 sig figs here. So that's 77 newtons. In which direction were we going? We were going east. So the force is 77 newtons east. This is the part where I pause and ask if there are questions. Hearing none. Let's do another question, another example. Where's the top of the page? There it is. Let's do example 4. I'm trying to kind of cover all the possible style of examples for you. Number 4 has got 2 parts, but it says during a road test, a driver brakes a 1,420 kilogram car. So mass equals 1,420. Moving at, oh, look at this. It's kilometers an hour. Moving at 64.8 kilometers an hour. The car slows down and comes to a stop after moving 729 meters. Okay, so VI equals 64.8 kilometers per hour. We need this in meters per second. So to do that, instead of kind of memorizing away, as I've mentioned before, I'd much rather you guys kind of understand. We want to go from kilometers to meters and hours to seconds. So 64.8 kilometers per hour is like kilometers over hours. So what that is, kilometers, 64.8 times 1,000, because there's 1,000 meters in a kilometer, over 60 minutes times 60 seconds. So that's how you would do the, I shouldn't use times, I should do it like this. This is how you would do the conversion. 64.8 times 1,000 divided by 3,600. So 64.8 times 1,000 equals that, divided by 60 equals that, divided by 60. 18. Well, that's a beautiful, look at how round that number is. There's no decimals or nothing. 18 meters per second. So VI is 18 meters per second. Need it meters per second. Mass is always in kilograms. Time is always in seconds. Displacement's always in meters. VF, car slows down, comes to a stop. So VF equals 0. Nice. So we've only got 2. We need one more thing here. Oh, 729 meters. So displacement equals 729. Now the velocity is west and the displacement is west. So it's all the same direction, which is nice. We don't have to worry about the signs. Except, we're going to have to find acceleration. Except, look at this. It's starting at 18, ends at 0. That means acceleration is going to be negative, which means it's going to be east. Something to be aware of. Okay? This question's probably going to tell us something else. Calculate the net force. Okay, so we've got to figure out what force is. First, acceleration. We're not given time. We don't need time. So we're going to use equation number 4. So that's VF squared equals VI squared plus 2AD. Final velocity is 0. VI squared, 18 squared. I think that's 326 or something like that. 18 squared, 324. 324 plus 2 times A times D. 2 times D, that's 1458. 1458 times acceleration. Let me just double check my math. 729 times 2, 1458. Bring 324 to the other side, so we're subtracting it from both sides. Negative 324 equals 1458A. Divide both sides by 1458. Our acceleration is going to be negative. 324 divided by 1458, 0.2 repeating. Another fraction. Acceleration equals 0.2 repeating. If you want it as a fraction, that's 2 over 9. So we have our acceleration. Now we need to get our force. Easy peasy for now. F equals ma. The mass of this car is 1,420. This is a car, right? Yeah. 1,420 times 0.2 repeating, or 2 over 9. Still in my calculator, so I just have to multiply by 1,420. 316. This is probably 2 sig figs. No, it's all 3 sig figs. So it's 316. 316 newtons. Now that acceleration, remember, I said it was negative. I didn't even write it in. That acceleration is negative compared to west, which means this is east. Okay? The opposite direction of west, it's negative, so its opposite direction is east. Don't get too hung up on like east is usually positive and west is usually negative. It's the opposite direction. 316 newtons east. That's the net force on the car. Oops, that was a little bit out of the page. There's a part B to the question though. What is the force of friction acting on the car while it is slowing down? Explain your reasoning. Okay, that's an interesting question. The net force acting on the car is what's slowing it down. Okay, the car is, there's a car. Look, it's a car. There's a window in front. So this car is going fast, and then it starts slowing down. So the net force is acting on the opposite direction. It's slowing it down. it's asking, what's the force of friction? The force of friction is what is stopping it. It's what is slowing it down. The force of friction is 316 newtons east. It's opposing motion. It's going in the opposite direction. This looks like some kind of code or something, doesn't it? SIGN or something. Friction is the force that is stopping it. There's friction that is applied to the brake pads on the wheel rotor thingy. You guys know how that works? I have barely an understanding. There's kind of the inside of the wheel, and then there's these kind of brake pads that get pushed into it to stop it from turning. It's friction that's stopping it. That's what's stopping the car. It's not like they just took their foot off the gas and rough roads or something like that. Those are the examples from page 133. I promised you some from page 135, so let's look at that. It's 3:30 right now. Why am I here? Page 135, because I'm not here Monday. Okay, number one. So I'm going to maybe show this first. So this, when we were talking about the notes, I said it was going to make sense once you see a diagram. Okay, so what the notes had said is the force. So if you look at this, there's going to probably no friction. Yeah, no friction is acting on the cart. So you've got this cart, and it's around a pulley attached to this weight. I don't want to put pen in the book. This is what is providing the force to pull this cart. F equals ma, 0.6 times 9.8. That's acceleration due to gravity. F equals ma, don't write in your textbook. F equals ma, 0.6 is the mass, acceleration is 9.8. That is the force acting on this whole system. Once you have the force, we're going to figure out the acceleration on this system. So the acceleration isn't just on this cart, it's attached to this weight, so it's the entire thing. So the acceleration the force based on this is going to be used on the entire thing. So then we do F equals ma again, except the mass for the second one is both of these together. It's going to be 1.8. Let's do the example. I'm hoping this makes sense. Clearly, I'm hoping. I'm going to see this on Tuesday when I get back and go, what the heck was that supposed to be? All right, so question number one says, calculate the acceleration of the cart in figure 7 given the following assumptions. A, no friction is acting on the cart. So we're going to do A first. Probably will help to have your textbook with you, in front of you, having a picture of it. If you don't have your textbook, go back to the video, just rewind a little bit and just draw it out quickly so you can see what's going on. Calculate the acceleration of the cart. So first of all, we have that F equals ma. We'll call this, let's call this 1. It's the first one that we're figuring out. The mass of the weight is 0.6. The acceleration is 9.8 due to gravity. So 0.6 times 9.8, I have no idea. 0.6 times is 5.88. So that is the force on this whole pulley system. Here's the cart. It's attached to a string, and then here's the weight. This is the 0.6. This bad boy over here is 1.2. So now for the entire system, so F2 or Fs, whatever you want to call it, mass is 1.8 because we're adding these two together. 1.8 times A, we have the force, I forgot. 5.88 equals 1.8 A. We're trying to figure out the acceleration, how fast are these things going to go. So we divide both sides by 1.8. 5.88 divided by 1.8 is 3.3. This is a 2 sig fig question. Yes. So the acceleration equals 3.3 meters per second squared. Okay, now notice it says, the question says calculate the acceleration of the cart. I paused there because this is going down. This is going to the right. We're not looking for the acceleration on this. We're looking for the acceleration on this. So it's going to be 3.3 meters per second squared to the right. If it was what's the acceleration of the weight, this would be down. This sucks not being able to see if you guys have questions or anything. B, a force of friction of 0.5 acts on the cart opposite to the motion. So what that means is, this is the net force in our situation, 5.88 minus 0.5, because there's 0.5 newtons of friction acting on this. So now our net force is 5.38, and then we just do everything again. 5.38, F equals ma. Divide both sides by 1.8. So it's going to be 3.0. We can't just say 3, we have to have two sig figs. So acceleration equals 3.0 meters per second squared. Still talking about the cart. So it's to the right. Okay, I don't need to do the second example, but maybe I'll talk about it for a second. Objects are placed on top of the cart as shown. Okay, so now this cart is 2 kilograms. This weight is 0.4 kilograms. So if we have the same questions, we're doing it the exact same way. It's just different numbers. Calculate the acceleration of the cart. Assume that no friction acts on the cart. So we do everything the same as we did in the first one. If you want to do this for yourself, the answer is there to check. What will happen to the acceleration of the cart if the mass of the objects on top of the cart increases? If this gets heavier, it's going to get slower. F equals ma. If we're solving for acceleration, F over m equals a. The bigger the mass gets, the smaller this number is going to get. Imagine the force is 1, just for the sake of argument. If this is 1,000,000, 1 over 1,000,000, that acceleration is going to be very small. If the mass is 1, the acceleration will be bigger. Okay, this was kind of in the notes, but now you're kind of seeing how it works. So what will happen to the acceleration of the cart if the mass on the object increases? The acceleration will slow down. What will happen to the acceleration of the cart if the object is taken from the top of the cart and tied to the hanging object? So we take this mass and we put it over here. Well, this thing's going to fly off the table. Someone's going to get hurt. That's what's going to happen if they move the mass from there to there. Because not only are you decreasing the mass here, you are increasing the force. Because instead of 0.4 times 9.8, you're going to have 2.4 times 9.8. That's all I got for you. I hope that makes sense. Hope I wasn't too much of a blabbermouth, fast-paced goose. See you Tuesday.